All right, gang, for this video, I've already created it, but we need to access the data set a little differently. So I'm going to show you how to actually access the data set, get it into StatCrunch, and then we'll transition into a video that I've already created. So if we go to, let's just go to STAT1800, obviously, and go to StatCrunch, and go to StatCrunch website, and just to open StatCrunch. Now, what I have is I have a data set that I will provide to you. It's called commute times, and it's on my desktop. So it will be included in Blackboard. It'll be right there under the resources for the course. So you'll click on it, download it, save it to your desktop, and do the following. So what I want to do is I want to go to data, and I want to load from a file on my computer. So I could just drag this over, or I could just go browse and select the file. It's a .csv file. Or again, I could just drag the file there and it will load it. All right, so I'm going to upload the file. And what we have commute times in Boston, New York, LA, Chicago, other big cities that we're going to examine in this video. So now we're going to transition to the video. Reasons that are important to me. My daughter is currently senior in high. Well, I have two daughters who are currently seniors in high school. It seems like one is going to probably stick closer to home. The other one is seriously considering a school in New York and another school in Chicago. So let's say I was, interested in the commute times in Chicago and New York, which I kind of am actually. So if I wanted, before I get into comparing those two, let's say that I wanted to just create a confidence interval for the commute times in Boston. So what I would do is go to Stat, again, come down to T-Stat, go to one sample, just like I did previously. But instead of with summary, I'm going to go select with data because, well, I have data, right? And I think I said Boston, so let's click it. Let's come down to the confidence level. And let's just say we want to do a 0.95. And I always just like to see the critical value, so I'll click that. So I can compute, and I see that there's a 0.95 probability that this interval from 29.5 to 31.9, I'm assuming these are in minutes. It'd be pretty crazy if it was hours. As impatient as I am, that would mean I would never go to Boston. So anyway, I'm sure it's minutes. So there's a 0.95 probability, or we are 95% confident that the commute time, that this interval contains the commute time. Now, let's say I'd like to compare New York and Chicago. So I'm going to go to, if I can get my mouse to work, to T-Stat, one sample with data, and I'm going to select New York and Chicago. Select my confidence level. I'm going to again keep this kind of the status quo of 0.95. I really don't need the Z critical, but I'm sorry, the T critical, but I'm going to get it. And I can compare. Now, when I look at this, I see that the Chicago commute time runs from 32.5 to 35.4, and the New York runs from 41.0 to 42.3. Now, what I've given you over here, we'll bounce over to where I'm kind of pointing now. So to compare mu1 and mu2, which I'm doing here, mu1 we'll just say is New York, and we'll say that Chicago is mu2. So I create a confidence interval for both. If the intervals overlap, then there's no difference. So when intervals overlap, it means something like this. If I have something that runs, confidence interval that runs from 14 to 28 and from 20 to 35, you can see that there is a segment right here where the intervals overlap. Well, in that case, I would assume that there's no difference in mu1 and mu2. However, if the intervals don't overlap, then we conclude there is a difference in mu1 and mu2. So I give you an example, but we can come over to this example and see that if we run from 32 to 35, there's no overlap with the interval running from 41 to 44. So we would conclude that commute times in New York are higher than commute times in Chicago. Now, I'm covering that because there's a question on your assignment, I believe, that addresses that issue. All right, uh, moving on, calculating sample sizes. Now, you're going to find quite a few similarities with proportions. So, meaning that just in general, if we have a confidence interval, we can find the point estimate by just adding the two and dividing by two to just find the average to get the center. Because remember, the point estimate X bar falls right smack dab in the center of the interval. So in this case, the center of that interval would be 93.41. So that's our point estimate. That's the value of X bar, the sample mean that we achieved from our sample. The margin of error, which again, depending on the textbook you use, can be a cap M, a cap ME, or just an E, is found by taking the big number minus the small number divided by 2. So 99.28 is the big number. It's the value to the right, 87.54 the small number in the confidence interval. So we get the margin of error to be 5.87. Now, here's the caveat. Since these T critical values change with our sample, and the critical value is an important piece in finding and calculating a sample size, we can only calculate sample sizes for n when sigma is known, and we use z's instead of T criticals. So again, it's just a caveat for obvious reasons. Again, the T critical depends on the degrees of freedom, which depends on the sample size, and the T critical needs to remain steady, sample, constant for us to be able to calculate in. So we must have the population standard deviation value to calculate the sample size. So let's say that we have a confidence interval that runs from 18.7 to 35.4. We know that the population standard deviation is equal to 9. So find in if the confidence interval is a 95% confidence interval. Well, the first thing I did is just on my calculator, I found the margin of error. And again, I found it by taking 35.4 minus 18.7 divided by 2. Now, the next thing I'm going to do is I'm going to do some algebra for you, creating an outcome that you're going to need. You're not going to be able, you are not going to need to be able to replicate the algebraic manipulation that I do here, right? I just want to prove to you where it comes from. So if I start out with the confidence interval formula, remember everything to the right of the plus and minus is called the margin of error. So if I want to ultimately, what do I want to do? What's my goal right here? My goal is to solve for n. So I want to get n by itself as a function of the other information. So the first thing I would do is divide both sides by z critical. The z criticals cancel out, as people like to say. So I have margin of error divided by z critical equals sigma over the square root of n. The next thing I would do is I would multiply both sides. I would actually divide both sides by the margin of error. So this margin of error will go away. I'm going to divide by the margin of error over there and multiply by the square root of n at the same time. There's a trick. Actually, let me just be completely transparent here. There's a trick that I'm using that says if you have a fraction, let's just say we know that 1/2 is equal to 5/10. And these things on the diagonal, means and extremes, they have uh, definite terms, okay? I can at any time switch these values. Put the 10 up here, put the 1 down here, and I do not change the equality. I could switch these two. So I could have the 1 over 5. Well, I'm losing my pencil. Um, I could take the switch these, so I could have the 1 over 5 is going to be equal to 2 over 10. So I can switch these things in the diagonal. Now, I can't if I'm multiplying. If I have 1/2 times, 5/10, I can't go switching stuff. But if I have a fraction equal to a fraction, I can switch these values. So that's really what I did here, is I switched the margin of error, put it down here. I took the square root of n and I put it in the numerator in the left fraction. When I get to here, what I want to do is I want to isolate the square root of n term. So I'm going to multiply both sides by z critical. So when I do that, I get the square root of n equals my z critical times sigma over the margin of error. Then I'm going to square both sides to get rid of the square root sign. So right here is what you need to be able to calculate the sample size for a confidence interval where the population standard deviation is given. Now, let's see how it plays out. For our problem, we have a z critical of 1.96. We have a standard deviation of 9, and we have a margin of error of 8.35. You can see when I get do the arithmetic there, I get like 4 point something. We always round up to the next integer. Now, this is a really small sample size. And it would be acceptable if we knew that our measurements were from a normal distribution. Sometimes in real life, you don't get these large sample sizes, which large sample sizes reduce the margin of error as we may want. For example, if I'm working for Mercedes-Benz and I want to, I don't know, look at maybe crash data analysis, I may not be able to go to the CEO and say, hey, give me, 78 of those, $250,000 Mercedes out there, so I can go out here and run them into a wall and see how they react in a crash scenario. I may be able to, have 5 cars or maybe only 3. So anyway, sometimes there's times where we can only conduct a study on a small sample size. Now, let's see what's going on here. The goal, let's construct a 95% confidence interval such that the sample mean is within 3 years. Well, I should just say 3 points uh, of the population mean. In other words, what we're saying here is we want the margin of error to be equal to 3. Well, it's just a simple manipulation of a formula now. 1.96 is and always will be the Z critical for the 95% confidence interval. If we wanted 90%, we'd put uh, another value there. If we wanted 99%, we'd put another value there. 1.645 for a 90% and 2.58 for the 99%. But we don't. We want 95. So 1.96 is and forever always will be the Z critical for a 95% confidence interval, multiplied by the standard deviation, which we know from previously is 9, and put in our desired margin of error, which in this case is 3. We get 34 point something. I don't know. Let me see. I think I actually did that right here. So 1.96 times 9 divided by 3 and quantity squared gives me 34.57, which always rounds up to 35. All right. Next thing, just proper interpretation. I see this. People just absolutely destroy the interpretation of a confidence interval. So I want to make sure you have this on your radar. Hang with me. Only 2 minutes left or so. Probably less than that. Probably 90 seconds. So first of all, before we get into the interpretations, remember, if we have a confidence interval like this, it is equivalently presented like this, or it's presented like this, where X bar is our 19, and this is our margin of error. And go ahead, go ahead and test it out. And you can see that 19 lies in the center, and 4.8 is the margin of error. Now, the interpretation, I gave you two. Which one do we think is correct? And I'll tell you right now, there's one that's correct and there's one that's not correct. So the first one says there's a 0.95 probability, or we're 95% confident that this interval contains mu. The other one, there's a 0.95 probability, or we're 95% confident that mu is contained in the interval. Now, at first glance, I believe these two look very similar, but it turns out that only one is technically correct, and that one is not it. Remember, our confidence level was used to create the interval. So our statement on our confidence level must be about the interval. We can't make a statement of probability on something we have no idea what it is. We don't know what mu is. So how can we determine the likelihood, the probability of getting something when we have no idea what it is? It would be equivalent to saying this: we have a standard deck of cards, right? Do something. What's the probability? Well, what do you want me to do? I don't know. Just do something. What do you want me to select, one card or two? It doesn't matter. Just do something. What's the probability you're going to get that? Well, you don't know because you haven't specified what you're doing, right? Same thing here. We don't know mu. We don't know what we haven't specified. That's what we're looking for. That's what these confidence intervals are all about. It's searching for this value and trying to estimate it. So not good. This, in my estimation, is perfectly reported. All right, gang, all I got. Take care.